Hello everyone. In today's session, I am going to discuss the concept of logic. Imagine you are designing a AI system that make decision on the basis of inputs, but how your system or program will comes to know that whether the information that is provided by you is true or false, that is correct or incorrect. Or just try to think on for a digital circuit, how a digital circuit is decide when the output is on or off. So welcome to the logic. These questions can be answered by using the concept of logic. We can call it as a mathematical logic too. In today's session, we'll discuss about the logic, what is a proposition, the different connectives we do have, what is a compound propositions, and what we mean by logical equivalence for two compound proposition or Boolean expression. Okay, so let us move on. Now, the first thing that we are going to discuss is what we mean by a proposition. Okay, proposition is the information or the input that you are giving to a system, and that information we say means our expectation is what, when you are giving an input to a system, that your system must identify it as binary output. Binary means what? One or zero, working, not working, true, false, right, wrong. So for that, the information that you are giving must be a proposition, must be a proposition. Proposition means what? A proposition, also called as a statement, is an information or sentence or mathematical expression which is either true or false, but not both. Okay, it must be either true or it must be or false, but it can't be comes in like sometime true, sometime false. If that scenario is there, sometime true, sometime false, we will not call it as a proposition. Okay, now let us try to take few examples on it. So the first one, if you see the first example which is there, 2 plus 3 equals to 5. Suppose that you give an input to the system which looks like 2 plus 3 equals to 5. Now the thing is that computer will take it as true, false, on, off, working, not working, 1, 0 scenario. If the system is able to understand it is true or false. So 2 plus 3 equals to 5. It is a mathematical equation and we know that it is true. It is true. So yes, we call this is a proposition. Okay. A information which is classify either true or false. Right? Either true or false, not both, is called as a proposition. Now, one more information we do have, which is close the door. Now, close the door. Can we say it is true? Think on it. Can we say it is false? Think on it. So we can't decide it is true or false. It is a kind of an order or instruction which is passed from one person to another one. So since we are unable to decide it is true or false, so this is not a proposition. This is not a proposition. One more example. Delhi is the capital of India. Yes, we know this is a proposition. Yes, it is a proposition because we are able to decide it is true or false. Do not make yourself confused between. I am not saying that a proposition is something which is always true. Okay, what I am saying a proposition is an information which is either true or false. It may a proposition is having its truth value as false. So this is true information. So yes, this is proposition and its truth value comes out as T. May God bless you. Once again, not a proposition because we can't decide whether this information is true or false. One another important example, X is greater than 10. Pause the video and think on it whether this is proposition or not. The answer is what? It is not a proposition. This information is not a proposition. Why it is not a proposition? Let us try to understand it. It is given that x is greater than 10. Now, can I say it is true? Can I say it is false? I can't say it is true. I can't say it is false. Why? Because it depends on x. It depends on the value of x. Suppose I take x equal to 4. So it comes out as 4 greater than 10. So now it is a proposition and the truth value for this proposition will be false. The truth value for this proposition will be false. In place of 4, if I take x equals to, let it be 15, in that case it comes out x is greater than 10. So in this case, it is also a proposition and the truth value is t. Okay, so this is how we can decide a information, a mathematical statement, a mathematical sentence, or a English sentence is true or false, or whether it is proposition or not. Now, when something is not proposition, we use the concept of predicates. Oh, that will cover at the last, that what is the predicate and how it convert a information in terms of proposition. Right now, this information is not a proposition. I hope it's clear to you why it's not a proposition, because we don't know that this information is true or false. Let us take one more example to be more clear. Suppose that this time I do have a statement which is x square, plus 1 is equal to 0. Can I say this information is proposition? Think on it, write the answer in the comment box. Now, x square plus 1 equals to 0 is not a proposition. Why not a proposition? Can I say this information is true? X square plus 1 equal to 0, is it true? No, we can't say. Can I say it is false? No, we can't say it is false. Why? Because it is depending on x and we didn't know that where x belongs to. Once we get it, suppose that it is given the value of x is this much, then it may be we are able to decide it is a proposition. Suppose I am taking x belongs to a natural number. X belongs to a natural number. So now can I say it is a proposition? So now you can put any natural number in this equation and it will always comes out as false. So in that case, this information comes out as proposition yes, with the truth value as false. In place of natural number, if I make it as integers, so in that case, we can also classify. So here we learn two things. The thing number one is what? Whether the information is proposition or not, it will decided by whether we are able to decide the information is true or false. Once the given information is proposition, then the second thing is that it's a truth value. If the proposition is true, we gives its truth value as t or 1. T or 1. And if it is false, we give its truth value as f or 0. So this is how we can understand about the proposition. I hope it's clear to you. Now, we do have some more example and we are supposed to think on them, they are propositions or not. So these are 1, 2, 3, 4, 5, 6 part. Try to think on by yourself and try to see whether you are getting the answers or not. Answer this question. Yes, it is not a proposition because a kind of questions we can't find the truth value. What about this one? Think on it. So is it true? We can't say it is true. Is it false? We can't say it is false. So yes, this is not a proposition. 5 plus 7 equals to 10. Is it a proposition? Yes, it is a proposition and the truth value is what? It is 5 plus 7, 12 equal to 10, which is not mathematically true. So the truth value will be f. So D part is a proposition with the truth value f. This is also a proposition with the truth value t, because 5 equals to 5. In the same manner, think on these two information too. Moving ahead, now we do have one another thing or another important point in the logic which called as a logic connectives or logical connective. Now, suppose that some of the propositions are given to us, 1, 2 or any number of proposition, and we are interested to find a compound propositions. Compound proposition. So logical connective are what? They are mathematical tool, or we can say they are operators which are used to find the compound proposition. If two propositions are given, how we can connect them? It is done by using the logical connectives. By using the logical connectives. So in short, we can say logical connectives are the tools or operators which is used to find a compound proposition, which is used to find a compound proposition by using the connectives. Now, if two propositions are given, how we can connect them? If two propositions are given, how we can connect them? That is done by connectives terms. So let us see what are the different connectives we have. For example, suppose that we do have P as a proposition, let it be 1 plus 1 equals to 11. Another thing, let us take one more, which is Q, and it says that, let us say, let us write some more thing, which is X, not X. We are supposed to make it as proposition. So let us take it as 2 is greater than 5. So we do have two proposition. First, make sure you are able to decide their proposition or not. 1 plus 1, 11. Yes, it is a proposition. Truth value, F. 2 is greater than 5. Is it is a proposition? Yes, the truth value is false. So these two propositions are given how to make a compound statement. Now these two can be connected by AND. So the resultant can be written as 1 plus 1 equals to 11 and 2 is greater than 5. One of the way to connect two proposition to make a compound proposition. In place of AND, we can use OR, we can use conditional, we can use biconditional. One more connective we do have, negation. So these are the 5 connectives that we do have. When we are connecting it by using AND, then this is the notation which is used for AND connective. AND is also known as the conjunction. OR is this one, which is quite similar to union, and is quite similar to intersection, and their meaning is also quite similar to those results. And means the intersection. So we will understand how it is similar to that later on. Or means one of them, which is similar to union, also known as the disjunction. We do have not, also called as negation, and this is how it is denoted by negation of P. If I am taking P as a proposition, we do have a conditional connective. This is how it is denoted, single line arrow, and this is what biconditional, this is how it is represented, the both side arrow. It is also known as if and only if. Conditional is also known as the type of if then. If then, if you get 90% marks, you will get a bike. If you get 90% marks, then you will get a bike. One of the example of making a compound proposition by using the connective, conditional, or implies, or if then. Now, when we make a compound proposition, that means a compound proposition is also a proposition, so it should have also its truth value. It should have also its truth value. So now when I'm talking about the AND connective, like we can use our common sense too. Like if two propositions are given and they are connected by AND, then the compound proposition will be true only if both of them are true, and this. So if both inputs are true, then the compound proposition comes out as true. For example, if I'm interested to find the truth value of this compound proposition, which is 1 plus 1 equals to 1 and 2 is greater than 5. So what is the truth value of this compound proposition? You can say it is false. How it is? What is the truth value of this one? 1 plus 1 equals to 1. So this is false. 2 is greater than 5. It is also false. So I am interested to find the truth value of false and false. So finally, false and false make it as false. Understood? This is how we can connect it by AND. In the same manner, if I am talking about the OR connective, so in case of OR, if any of them is true, then the compound statement comes out as true. If any of them is true, then the compound proposition comes out as true. Or we can call it as if we do have multiple proposition. If at least one of them is true, the compound proposition comes out as true. Negation, that means the not of the original information. If information is true, its negation will be false. If information is false, its negation will comes out as true. Now, talking about conditional and then biconditional, let us move on for their truth value. So now I'm going to discuss that if a compound proposition is given, how to find its truth value. So this is for AND. If your input is T, the output is T. If this is T, this is F, it will F, it will F, it will F. You can see it comes out as true only in the case when all the information or all the inputs are comes out as T. So this is how you can remember for the AND connective truth table. T only if all inputs are T. F otherwise. Suppose that you have designed a logic circuit which do have a multiple switches, multiple proposition we can say. So AND means what? The circuit will work properly if all the switches are on. Understood? This is how we can understand in terms of application or in terms of generating some system. If it is having n number of switches and if any of them is not on, then the output will always F. This is what exactly what we mean when all the input is T, the output is also T in case of AND connective. Now we want to reverse it. We want to design a circuit which will work if any of the switches are on. If we do have n number of switches, if we do have this is one of the switch, this is another switch, and we do have such n switches. And we want that the circuit will work if any of them is on. Any of them is on. So that can be done by using the OR connective. By using the OR connective. So combine all the proposition, make a compound proposition of all the proposition by using OR connective, which is later on connected by OR gate also. So it can be on from anywhere, just on any of the switches and the circuit will work. Suppose that there is a display and it is controlled by n number of individual. Control means only to on. How to off, that will be discussed later on too. So if any of the individual on the switch, that display will work. So this is how we can remember for OR connective, it will always be T if at least one of the information is T. And in what case it will false? False means not working or zero. So if all of them will off the switches, then only it will not work. Comparing to the AND connective, it will not work if any of the individual off their switch. I hope now it's clear to you, connective OR and AND. In case of OR, at least one T will make it T. At least one on will make the system is on. In case of on and all of them must be working in case of the working of circuit. So as per requirement, the proper connective which is later on extended to the gate is supposed to be used. Moving on for the conditional, quite interesting, and we are supposed to pay attention on it. So it is kind of situation if then. If then, we are supposed to remember this case only. We are supposed to remember this case only. So if we are talking about the conditional proposition, if we are talking about the conditional connective in terms of compound proposition, it will comes out f only when your if is true and then is false. If is true, do remember over here, in and or connective, order does not matter. Means what? Whether I am writing p and q or I am writing q and p, they are giving the same output. But when talking about the conditional, if I am writing P implies Q and I am writing Q implies P, they are not same. They are not identical, or I can say not logical identical. Okay, so be careful with this term. Now let us try to accept this case. It is every time T. I am going to connect it with the same example that I have given in initial phase of this video. If you get 90% marks, you will get a bike. Okay, so suppose that you get 90% marks and you get bike. P is for 90% and Q is for the bike. You get 90%, you get a bike. So what is the truth value of the this compound scenario? True. That means correct. Now you get 90%, but your father says that, or the one who promised you will get a bike is not agree to give you a bike. Then in this scenario, what happened? You will say, no, it's not fair. It's not working. That means in this scenario, it will comes out as false. The output is false. Now, the last two are quite interesting in terms of computer language. If your input is not true, the first string is not true, you didn't get 90% marks and your father didn't give you bike. Yes, no problem. Fair enough? True. If you didn't get 90%, still your father feel, let us give them bike to motivate them for the further classes. Still in this case, it is true. Understood? So that means when I'm talking about P implies Q, it is important that what is the truth value of P. And if P is false, then does not matter what is the truth value for Q. It does not matter what is the truth value for Q. The final output will always comes out as T. Make it as highlight, because many times many students did it wrong when term or taking in terms of F, P. The next connective that we do have is called as the biconditional connective. So what it did, it is what in both the way. If then is one way, and if and only both the way. If P then Q, if Q then P. So it will comes out as T when your all the input is of the same nature. That means either all the inputs are T or all the inputs are F, then only these are the cases when a biconditional compound statements gives you the truth value of T. In another word, we can also understand it. We can also understand like if inputs are not of the same nature, then the output is always false. If you are connecting your proposition by biconditional connective. So these are the few of the connectives. I mean, almost all discussed. One left is negation. So how to make the truth table for negation? So if it is T, it will comes out as F. If it is F, it comes out as T. So this is how P and P negation table can be seen. Okay, I hope you understand it. Moving on. Now, when we are making the compound statement, there are 3-4 terms which comes in the picture quite repeatedly and quite having the quite significant role in the logic, mathematical logic. They are tautology, contradiction, satisfiable, and contingency. So we called a compound proposition as a tautology. We called as a compound proposition as a tautology if it will always work. It will always work means what? If I am making the compound proposition as R, then its truth value is always T. Does not matter what inputs you are giving to the system, on, off, 1, 0, true, false, it will always true. Then such compound proposition is called as a tautology. A tautology, many time also known as a valid statement, is also known as a valid statement. We'll take the example on these terms also. Now the contradiction, opposite of tautology, that means in tautology we are saying that its information is always true. In contradiction, we are saying the compound proposition final truth value is always false. If always false, a contradiction is there. We call it as a contradiction or not valid statement. Tautology, always true or valid. Now, two more extension is there for these terms, which is contingency and satisfiable. If the truth value of the compound proposition are the combinations of the true and false. Few of them is true, few of them is false, even though there is not any specific quantification that how many of them is T and how many of them is false. It is simply written that it is a combination of T and F. That means it may there is one T and rest of them F, 2T, rest of them F, 1F, rest of them as T, means at least 1T and 1F. We can understand it like this. If at least 1T and 1F is there, we called it as contingency. The compound proposition called as a contingency if the final truth value for this compound proposition is the combination of few T and few F, or at least 1T and at least 1F. Many students understand it in terms of like it do have 50% T, it do have 50% F. There's not any specification or quantification for how many true or how many false should be there. Talking about the last term for these things, which is satisfiable. So compound proposition is called satisfiable if at least one combination of input is there whose output is T. That means the final column of the truth table must have at least one T. Then we called it as satisfiable. In satisfiable, the different author do have different approaches. Like few of them says we are supposed to get one combination of input which gives the output as T. Some author says that at least one combinations of true inputs. Right? If two propositions are given, both of them is T, then the final column giving them T is called as a satisfiable. Both of them is acceptable as it is there in literature, in logic. So satisfiable at least one T. Now the relation between these two or these four. So can I say every tautology is satisfiable? The answer is yes. For satisfiable, I need at least one T. In tautology, everything is T. So task is done. At least T means what? All of them can also be T. So every tautology is satisfiable. Coming back to the reverse picture, can I say every satisfiable is a tautology? The answer is no. So I am having a compound proposition whose output, let it be F, T, F, and T. These fours are there. So at least one T task done. So it is perfect satisfiable, but it is not a tautology. So every tautology is satisfiable, but need not to be vice versa. Every satisfiable is not a tautology. Can I say every contradiction is satisfiable? So the answer is no. So the answer is no. Can I say every satisfiable is contradiction? The answer is no. Now the relation between these two. Can I say every contingency is satisfiable? The answer is yes. Answer is yes. Why it is yes? In contingency, we do have at least one F, one T, na? And this is the definition of satisfiable. So every contingency is satisfiable. So this is how we can find the relation between one and another by using the definition. Okay. Now moving ahead for logical equivalence. Logic, I will take the example on tautology, contradiction, and those four terms after this logical equivalence. Okay. Now the logical equivalence means what? We do have two propositions and we are supposed to check whether they are equivalent or not. Not exact equivalent, logically equivalent or not. So in terms of logic, we call two propositions are logically equivalent if they gives the same final output. There are two circuits. Circuit means a compound propositions, a combinations of different propositions. Two circuits are there. Both the circuits are called as logically equivalent if their final output comes out as same. If their final output comes out as same, does not matter what the inputs you are giving to the system, the corresponding output should comes out in both the cases. Then it does not matter whether the propositions are same in actual or not. For example, suppose that I do have a proposition which looks like P implies Q. One of the proposition having two individual P and Q connected by implies a compound proposition. And I do have negation P and negation Q, one more proposition. The structure of these two propositions are not same. It is having conditional, it is having and, it do not have negation, it is having negation. So we call them as a equivalent proposition, equivalent compound proposition if they gives the same truth value. Means what? Let us try to make a truth table for this one. So we do have two inputs. For two input, how many? For two proposition, how many possible out inputs is there? 4. 2 times T, 2 times F, T, F, T, F. So number of inputs for a compound proposition is 2 power n, where n is the number of proposition that compound proposition is having. So P implies Q is having two proposition. So total 2 power 2 is 4. So this is how 4 is listed. You can write them in any order, but try to remember, try to take care. None of the inputs are going to be repeated. None of them should be identical with others. And we can do it in a neat and clean manner. If total 4 is there, in the first column, write 2 times T, 2 times F, then alternate T and F, 1 times T. If in place of 2, I do have 3 proposition, so total will be 2 power 3, that is 8. So how to write 8? So P, Q, R. So now for 8, we'll start with 4 times T and 4 times F. 4 times T, 4 times F. Then do its 50%, 2 times T, 2 times F in the repeated manner, then 1T, 1F, 1T, 1F. This is how we can combine all the inputs. Back to the problem. Now making a column for P implies Q. So remember implies column, implies connective. The output comes out as F when T implies F, otherwise always T. So where is T implies F? This is T implies F. Otherwise, it always comes out as T. So this is we call as the final column of the compound proposition P implies Q, and we are going to compare it with this one. Okay, now let us make negation P. One more column I am going to make negation P. So opposite of P. So T opposite is F. This is also T. So F. This is F. This is T. This is F. This is T. Now I want to connect negation P with Q with AND connective. So merging this column, merging negation P with AND connective and taking the other column as what? This Q. So merging this and this with the AND connective. What is AND connective if you remember? Everything is T, then it will be T. So the first one, this is T, this is F, so it is F. So this is F, this is F, it is F. T and T, it is T. F and T, it is F. So now this is the final truth value of these two compound proposition. So I want to compare between what? This one P implies Q and this one. So are they comes out as identical? This is T, this is F. Not same. This is F, this is F, same. This is T, same. This is T, this is F, not same. So we'll say they are not logically equivalent. 3 parallel lines, symbol for equivalence. If I crossed it, not logical equivalent. So I can say negation P implies Q is not logically equivalent to negation P and Q. Understood? Now, this is how we can check two logical or two compound propositions are logically equivalent or not. Now, if I want to check this P implies Q, is a tautology, contradiction, satisfiable, or like contingency? It is not contradiction because not all of them T. It is not contradiction because not all of them F. Is it contingency? Yes, at some T, some F. It is satisfiable? Yes, at least one T is there. Okay, so this is how we can understand two propositions are logically equivalent or not. Okay, now let us say, is there any other example? Let me check it. Okay, so this is one example which is given in place of and, it is given as or. So if we make the truth table for or connective, then let me check it whether it comes out as true. Taking reference of that slide, negation P or Q. So negation P merging with Q. So first one is T, second is F, third is T, and fourth is C. So what I get? T, F, T, T. And it is same as the truth table which is there for P implies Q. Now you can see the corresponding truth value comes out as same. So yes, now we can say P implies Q is logically equivalent to negation P or Q. Negation P or Q. Understood? So this is how we can check whether two compound proposition are logically equivalent or not. I hope you understand the concept of propositional logic, and you understand how we check the truth value for a compound proposition. That's all for the session. In our next session, we are going to discuss about the normal forms, okay, which is having quite significant important role in in I can say when we generate some compound proposition, and if it is in some specific form which we call as normal form, then it's quite easy to evaluate it, quite easy to find its truth value whether it is working or not. Okay, so let us close this session.